Remember that Fermat's principle stated that a ray will follow the path between 2 points that takes the least time. In refraction, you have to take into account what we call the optical path length. Because light slows down in a higher refractive index, it will take longer to go a particular distance, and so we say that the optical path length is bigger. So in any medium, the optical path length is the actual distance multiplied by the refractive index. Now look at the diagram of a ray going from A to B. If it was just one medium, the ray would have to go in a straight line. But because N2 is bigger than N1, the shortest trip is actually one where the ray spends more time in medium 1 than in medium 2. The bigger N2 is, the shorter the distance the light will travel on that side of the boundary, so the angle of refraction gets smaller and smaller. You can find online a complete geometrical construction going from Fermat's principle to Snell's law, but we don't have time to do it here. Now this is what a real situation looks like with a ray hitting the block. So even when there is refraction, there always has to be reflection at a boundary. Then there may be refraction as well. Total internal reflection is something you've looked at, but it's a confusing term for students because it is in fact an example of refraction. We know it's refraction because whether it happens and at what angle depends on the index of refraction of the materials either side of the boundary. Now remember that this is something that can only happen to light that reaches a boundary going from a higher refractive index to a lower refractive index. There are some sample rays in the block that you can see there, and they are all bending away from the normal. That means the angle of refraction is bigger than the angle of incidence. If we look at the rays numbered 1 to 5, the angle of incidence is increasing, so the angle of refraction must be increasing faster, and it reaches 90 degrees while the angle of incidence is still something less than that. The 90-degree refraction angle is shown as ray 4, and the angle of incidence that leads to that is what we call the critical angle for that material. So for any angle bigger than the critical angle, there will be no refracted beam at all, and all of the light goes into the reflected beam. Here's a pretty example of total internal reflection. Light from further away in the water has headed upwards, bounced off the surface of the water because it was at more than the critical angle, and then travelled to the camera. Note that this is actually a better reflection than you get from an ordinary mirror. Any ordinary reflecting surface will actually absorb a little bit of the light, so the intensity of the reflected beam will never be quite as high as the incident beam. But with total internal reflection, sometimes just called TIR, it really is 100% reflecting. There is no absorption. That's what makes TIR such a good effect to use in optical fibre communication. Optical fibres are made from very high quality glass in a tiny fibre, maybe 100 microns in diameter. It is surrounded by a cladding that is made of a material with a lower refractive index. If you teach this to students, be aware of a very common misconception. Many students will remain convinced that the fibre is really a hollow tube made of glass that has air in the middle, and that the light bounces down the air in the middle of the tube. But in fact, the core has to be solid glass or the total internal reflection wouldn't work. The core and cladding of a fibre are then surrounded by a plastic jacket that protect it and keep it from being bent too much, which could snap the fibre.